Zachary Dayton.
And I'm Quinn Stewart, and today we're going to be talking about dark matter and dark energy.
So class, do any of y'all know what that is?
Well, actually, more is unknown than is known about dark matter. We know how much dark energy there is because we know how it affects the universe's expansion. Other than that, it's a complete mystery. But it is an important mystery. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth, everything observed with all of our instruments, all normal matter, adds up to less than 5% of the universe.
One explanation for dark energy is that it is a property of space. Albert Einstein was the first person to realize that empty space is not nothing.
The first property that Einstein discovered is that it is possible for more space to come into existence.
Then, one version of Einstein's gravity theory, the version that contains a cosmological constant, makes a second prediction. Empty space can process its own energy. Because this energy is a property of space itself, it would not be diluted as space extends. As more space comes into existence, more of this energy of space would appear. As a result, this form of energy would cause the universe to expand faster and faster.
We are much more certain what dark matter is not than what we are it is. First, it is dark, meaning that it is not in the form of stars and planets that we see. Observations show that there is far too little visible matter in the universe to make up the 27% required by observations.
Second, it is not in form of dark clouds or of normal matter. Matter made up of particles called baryons.
Very honest.
Oh my god. We know this because we would be able to detect baryonic clouds by their absorption and radiation passing through them.
Third, dark matter is not antimatter because we do not see the unique gamma rays that are produced when antimatter annihilates with matter.
Finally, we can rule out large galaxy-sized black holes on their basis of how many gravitational lenses we see. High concentrations of matter bend light passing near them from objects further away, but we do not see enough lensing events to suggest that such objects to make up the required 25% dark contribution.
Unlike normal matter, dark matter does not interact with the electromagnetic force. This means it does not absorb, reflect, or emit light, making it extremely hard to spot. In fact, researchers have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter.
Dark matter seems to outweigh visible matter roughly 6-1, making up about 27% of our universe.
One idea is that it could contain supersymmetric particles, hypothesized particles that are partners to those already known in the Standard Model. Experiments at the Large Hadron Collider may provide more direct clues about dark matter.
Many theories say the dark matter particles would be light enough to be produced at the LHC. If they were created at the LHC, they would escape through the detectors unnoticed. However, they would carry away energy and momentum, so physicists could infer their existence from the amount of energy and momentum missing after a collision.
Dark matter candidates arise frequently in theories that suggest physics beyond the Standard Model, such as supersymmetry and extra dimensions. One theory suggests that the existence of a hidden valley, a parallel world made of dark matter having very little in common with the matter we know. If one of these theories proved to be true, it could help scientists gain a better understanding of the composition of our universe and, in particularly, how galaxies are held together.
Dark energy makes up approximately 68% of the universe and appears to be associated with the vacuum in space.
It is distributed evenly throughout the universe, not only in space, but also in time. In other words, its effect is not diluted as the universe expands. The even distribution means the dark energy does not have any local gravitational effects, but rather a global effect on the universe as a whole. This leads to a repulsive effect, which tends to accelerate the expansion of the universe. The rate of expansion and its acceleration can be measured by observations based on the Hubble law. These measurements, together with scientific data, have confirmed the existence of dark energy and provided an estimate of just how much this mysterious substance exists.
Only 5% of the universe is visible. What is the rest of it made up of? Dark matter could also explain certain optical illusions that astronomers see in the deep universe. For example, pictures of galaxies that include strange rings and arcs of light could be explained if the light from even the most distant galaxies is being distorted and magnified by massive invisible clouds of dark matter in the foreground, a phenomenon known as gravitational lensing.